continue to talk. So I'm going to talk about the Teichmuller distance. So it's a metric, or Teichmuller distance or metric. So now we return to the situation of the Riemann surface. So we have two Riemann surfaces. So you have Riemann surfaces R and R prime, and assume they are homeomorphic as a topological space. So they can be regarded as two different complex structures on the same closed surface. So a map from a homeomorphism F from R to R prime is said to be K quasi-conformal if looking at this, if you look at this map by, via chart, so I mean for chart phi for R and psi, well, maybe it's better to put it like psi for R and phi for R prime. Then if you have a code, so what that should be the looking at this. Oh my, maybe I like phi to be here. So if you look at this map using the chart, then the phi, it's a chart for the R. So you have a map from some neighborhood of some point to a region in a complex plane. That's a local chart. And then compose psi. So you have a map F here. So the R prime is here. So you have a point here, and you have a local chart psi here. So if you consider the composition like that, and restrict the domain of the definition as some smaller one, then you have a map from the region in a complex plane to another region in a complex plane. So if this is always K quasi-conformal, then this homeomorphism is said to be K quasi-conformal. Okay. So let me tell you this. So this definition looks like depending on choice of the chart, but it's not, because if you change the chart, well, if you change the coordinate, then it's just composed by some holomorphic map. Okay. So you have so if you have so suppose H is holomorphic, then so the changing the chart is the composition something like, well, F should be so it's something like G is quasi-conformal and H is just homomorphic map, then as I told you, it's something like that. But this is 1 because it's a holomorphic. So it's just less than that. So if you consider the H inverse, then you have this should be you also get that. So that they are equal. So changing chart doesn't affect this number K. So and this is kind of well defined. So so if the homeomorphism is K quasi-conformal, if you look at that from using the chart, then it's said to be quasi-conformal. Okay. So the Taichimura did was to find so for a given two Riemann surfaces and give some homotopy class of homeomorphism or isotopy class of the homeomorphism. He tried to find the quasi-conformal homeomorphism with smallest maximal dilatation, and he actually found the what is the smallest one, what is the most efficient map between the two Riemann surfaces. So before stating his theorem, so let me define the Teichmüller distance or Teichmüller metric on Teichmüller space. So suppose you have 2 points in a Teichmüller space. So Teichmüller space consists of pairs of Riemann surface and homeomorphism from S. So suppose you have 2 points, 2 pairs in the Teichmüller space. So we don't have a topology yet, so it's just a set. But then we define the distance. So suppose x1 is this point, the x2 is at this point. Then we define the distance between x1 and x2 to be the infimum of quasi-conformal map. So it should be 2 composed by F1 inverse. So it's a map from sigma 1 to sigma 2. So the infimum of the dilatation of quasi-conformal maps, maximal dilatation of the quasi-conformal maps, homotopic to this composition. So recall you have a homeomorphism from S to R1 and F2 from S to R2, and you consider the composition like that, and try to find the infimum of the maximal dilatation between maximal dilatation of quasi-conformal maps homotopic to that one. Okay. Or maybe, sorry, it's a distance, so it's not still distance. So to make it distance, you should take a log. And the half is not so important, but it's a so ordinarily you put half there, so that this should be the this should be the infimum of the log of k of the g. Okay. Okay. So then this becomes the distance between the points in 2 points in the Teichmüller space. So let me show you, give you a sketch of the proof of the fact that it is really metric. So the lemma defines a metric on TS. So this should be a distance function. So the first thing, well, this should be number 0. So the first thing should be that this can be defined. So if there doesn't exist a quasi-conformal map homotopic to that, then you cannot define this number. So it's just, it should be something like infinity. So that's not good as a distance function. So the first thing we have to check is it's always less than infinity. It should be a finite number. So, but this is easy to check if you use the fact, well-known fact that any homeomorphism can be approximated by a diffeomorphism. So this is just a homeomorphism, can be approximated by diffeomorphisms arbitrarily closely. So, so take G close to F2, F1 inverse, because they're close. If that map is close enough to that one, then they should be homotopy. But if G is a diffeomorphism, then you can just calculate the derivative, and because S is compact, it's bounded. So both the number like both this and this that should be bounded, and this should be away from 0 because it's a diffeomorphism. So the inverse is also differentiable. So so the ratio is bounded. So that should so if it's differentiable, then kg must be finite. So you have at least one quasi-conformal map. So the diffeomorphism is always quasi-conformal on a compact Riemann surface. So you have some number. So you have at least some finite number here. So this should be finite. Okay. So the second thing we have to check is that if this number, this distance is 0, then the 2 points should be equal. So this is not so easy, but it's a kind of exercise of the complex analysis. So you have it's not exactly complex analysis, but it's like some exercise of some analysis. So this means this infimum is 0. So that means the infimum of this number is 1. Okay. But you don't know if it's realized. This number 1 is realized by some map. So you just have a sequence of quasi-conformal homeomorphisms, so whose maximal dilatation tends to 1. So what you should do is to make it converge to some map. So that's the point of the proof of this one. And but you can do that, and the limit is conformal homeomorphism. Conformal means that the holomorphic homeomorphism. So that's if this is conformal, then it's the 2 points were defined to be equivalent. So the equivalent. So that means the 2 points are the same. So so that's a proof. Okay. So you need a convergence of QC maps. So to a holomorphic map. So for that you need some criterion convergence like Ascoli-Alzheimer's theorem like that or something like that. So that you need some kind of the analysis here, but anyway, so you can do that. So and the third one is a triangle. Or the symmetry is easy. Actually, I haven't told you this, but you have a equality like that. So if you consider inverse, then the maximal dilatation is the same as the original map. So that can be somehow easy. So if you map the circle to some ellipse, then to make this ellipse back to the circle, you need the same number, so same distortion. So this is the meaning of this equality. So you have that. So that this implies that the distance is symmetric. And then the third one is a triangle inequality. So so that should be so you have 3 points in the Teichmüller space. And then you consider the infimum. So so this should be x1, this is x2, this is x3. So what you'd like to know is the distance between x1 and x3, which was defined to be the infimum of the half of the log of the dilatation of quasi-conformal map homotopic to so the K should be QC homotopic to F3 composed with F1 inverse. Okay. So that should be K. Yeah. Then it's less than or equal to so if you have a map from sigma 1 to sigma 3, then you can consider composition of 2 maps like that. Then the set might be smaller if it's expressed as a composition of 2 maps. So that means the infimum might be a bit bigger, but anyway, that you have an inequality like that. So that you have a composition of the 2 quasi-conformal maps like that. The one is homotopic to the F2 and F1 inverse and F3, F1, F2 inverse. And this is a composition of the so H and the G. Okay. And this one is bounded by the product of these 2 by lemma. So you have infimum G F1 inverse log K G, Kg plus, because this is the product and you have a log here, so you have plus the half the H homotopic to F3 F2 inverse log H. Okay. So this is equal to the Teichmüller distance between x1 and x2 plus x2 plus x3. Okay. So this is the triangle inequality. So now I have proved that this is really a distance function, and the Teichmüller space has a metric. And this metric is just called the Teichmüller metric. So now we have, so because it's a metric space, you have a topology on the Teichmüller space. So with respect to that topology, it's known that the Teichmüller space is homeomorphic to a Euclidean space of dimension 6G minus 6. So the maybe I'm not going to prove that, but this turns out to be homeomorphic to 6G minus 6 dimensional Euclidean space. Actually, if I show the existence of something called the Teichmüller map, then this is a kind of corollary to that. So now let me turn to the Teichmüller map. Okay, 1.4. So this is just related to the problem of finding the most efficient quasi-conformal map between two Riemann surfaces, provided the homotopy class is fixed. So actually, so Teichmüller found that there is a unique quasi-conformal map attaining the smallest maximal dilatation. So that's in other words, this infimum. Where is the definition? Well, maybe this is the definition. So actually, so he found that there is a homeomorphism, quasi-conformal homeomorphism attaining this infimum. So that means this can be replaced with minimal. So you have a map attaining this infimum. So that's what Teichmüller found. So this is a theorem by Teichmüller. So for any 2 point in a Teichmüller space, you have there exists a unique quasi-conformal. Probably it's yeah, quasi-conformal homeomorphism G from sigma 1 to sigma 2, homotopic to this one, such that the maximal dilatation of this map is just the distance between these two. So in other words, for any other H quasi-conformal homeomorphism, homotopic to H2 by H1 inverse, the KH must be larger than KG. So this map is called the Teichmüller map. Okay, is it okay? Is the definition clear? So there is a unique map. So the definition. So that actually there is a map from sigma 1 to sigma 2, homotopic to that one, which attains whose dilatation. Sorry, this should be. Okay, because it's a distance. So obtain the best value, so the infimum of the maximal dilatation. Okay, and actually the Taichi-Miura constructed such a map concretely. Gave a construction of the Taichi-Miura map. So it's not a abstract existence theorem. So he actually constructed a map. So to define that, so let me just look at the complex dilatation again. So let me recall you that there was something written as mu, which is a ratio, which is a ratio between the derivative at the direction z bar and the derivative at the direction z. Okay, so now we'd like to consider that map on a Riemann surface. So you have a Riemann surface sigma 1 and a Riemann surface sigma 2. And suppose you have a map G, quasi-conformal map G. So this is QC. Now, consider the covering, universal covering. Of this one, sigma 1. So the uniformization theorem, Riemann uniformization theorem tells us that because this one has genus greater than 1, so this should be the upper half space. This is the upper half space. No, it's not half space, half plane in a C. And so if you have a map from sigma 1 to sigma 2 G, which is G, and then you have a covering of sigma 1 by U, then you can lift this map to G tilde. It's just a composition of a projection, covering projection, and a G. So let us calculate how the so you have a mu of GZ, which is this one. It's GZ bar over GZZ. Okay. And we'd like to calculate how it changes so you like to calculate the mu of this one. How this changes with respect to the covering translation. So you have a covering translation of the pi 1 numbers here. So you have a gamma here, and then it acts as a translation on the covering. So because this is just a lift of the map, so let me just calculate how it changes. So because this is defined to be mu, probably this mu G tilde at the Z. Now we are considering the Z in the upper half plane. Then it's just wait a minute. So yeah, so it's a differential derivative of this one divided by this one. So that's the definition. Okay, and because this map, so this is a covering translation, and if you translate a point to another point, then they project it to the same point here, and its value by g is the same. So if you just, this should be the g2, so the composition is the same map here, so it's just something like that. Now, you can calculate the derivative of the composition of the function. So you have a gamma and this. So you just calculate that. Then it's the derivative at that point, and then no, it's because it's bar, and this should be bar. Okay, that's it. Okay. So and here you have the same kind of calculation. Then this should be that one. Okay. And so you have a mu at the point gamma z and times like that. So you have a rule of the kind of the transition. So so you have so the rule is like that. So that this should be the complex dilatation of the map from U. So to be more precise, we are considering the local chart here, but because it's the same local chart, we just write it as sigma 2. So it's the rule is something like that. So this should be the mu z. Okay. So conversely, if you have a complex dilatation function defined on U with that rule of the transition, then you get the complex dilatation here. So the complex dilatation on sigma 1 is nothing but complex dilatation on U with this rule. Now, I'm going to introduce another notion of which is homomorphic differential. So it's homomorphic quadratic differential. So the homomorphic we are considering upper half plane, and it's a map from function from U to C, which is a homomorphic. So it's said to be or called homomorphic quadratic differential if this rule holds, so that this should be the you have a, so the situation is like that. So you have a covering of sigma 1 by u. So you have a holomorphic quadratic differential on sigma, probably sigma 1 or maybe sigma would be better. So you have a universal covering of Riemann surface sigma by the upper half plane. So because it's covering, so the pi 1 of sigma acts on there. Then, so for any pi 1, any element in pi 1, if you have a equality like this, so you times is equal to that one. So it's it looks a bit like this kind of rule. So although the what you have to multiply is different. So here you have something like that. So here you have just a square of the derivative. Then it's called holomorphic quadratic differential on sigma. So another way to define it is just so this is just same as this defines differential form on holomorphic differential form on sigma. Actually, this is a lift of that one to U. Because so if you have a holomorphic differential form in U, then lift it to phi tilde z square. Then because this should be invariant with respect to the action of pi 1, so this should be equal to that one. Okay. So that means so you have a gamma here. So you have the derivative of gamma square here. So now you have something like that. So this should be equal to that. So this is just the equation here. So this is nothing but the lift of this coefficient of the differential form, holomorphic differential form of degree 2. Okay. So what Teichmüller was to construct a complex dilatation function using holomorphic quadratic differential. So the theorem, this is due to Teichmüller. So let phi be holomorphic quadratic differential on Riemann surface sigma. Well, maybe sigma 1 this time, because we'd like to consider Teichmüller map. Then then there exists quasi-conformal homeomorphism from sigma 1 to some Riemann, another Riemann surface, sigma 2, such that the complex dilatation of this quasi-conformal map. So well, and you should give some k, which is between 0 and 1, not including 1. Then there exists quasi-conformal homeomorphism such that complex dilatation is equal to this one. So this was defined to be the okay. And this F is the Teichmüller map. From sigma 1 to sigma 2. Well, the homotopy class should be the well, fixed, but this F is given with some homotopy class. So, I'm not talking about the homotopy class. So using this F, so this should be the Teichmüller map from sigma 1 F1 to sigma 2 F1. Okay. So I'm not going to prove that. So just explain the meaning of this. So we start from a affine map again. So suppose you have a z coordinate and a w coordinate. So both for the complex plane. And suppose you have an affine map expanding the real axis by k, which is greater than or equal to 1. So that means x plus iy is sent to k times x plus iy. Okay. So in this coordinate, in complex coordinate, it should be written like k plus 1 z plus k minus 1 z bar. Okay. Now, we'd like to look at the Euclidean structure here. So because you have a complex number, if we identify it with two-dimensional Euclidean space, that is a Euclidean plane, then you get some metric. So Euclidean metric here, so the w, the absolute value of the w square, so that's a Riemann Euclidean metric. Is regarded as a Riemann metric on C. Then it's just the omega times dw times dw bar. Okay. So now, because w is like that, so okay, dw dw is also, let me just it's just half of I dy, and the dw bar is half of the, okay. Oh, maybe I don't need a half. Half is not necessary here, sorry. This is just that one. W. Sorry. So this should be Z. So, but anyway, so the so this should be X Z, but okay, Z bar. Okay. So now dW. So dW is like that. So dW is you can express it using that. And the dW bar, again, you can just take in bar and take d. So then you can calculate it as this, and it's something like this. Where k is equal to the k plus 1 over k minus 1. K minus 1 over k plus 1. Okay, so the coefficient here is just a square, but here you have a k minus 1 square, so that it's like okay. So this is the pullback of the Euclidean metric on Z plane. So it looks like it's expanded in Z bar direction by k. So this is just a scalar multiple. So it's just a changing of scaling. So the distortion comes from this number k. So now we'd like to pull back this picture by some homomorphic map. So because we would like to consider the local chart, so that we have some region U and homomorphic map from U to Z locally. And then we'd like to pull back this form by psi. So Z is psi zeta, where this is have a zeta coordinate. Okay. Then so this is homomorphic. Then you have that dw square, and it should be something like that. Square. And now, so the z is okay. So so you have then you have the same scalar here, and then you have something like that, and but you have a absolute value squared, so that you have something times zeta. So this is this part, and that part should be the change something like this. So you have absolute value square here, so you divide it by this one, and the transition should be something like so. Yeah. Right. Okay. So this one of square. This is actually is a quadratic holomorphic quadratic differential. If you have if psi is the chart, if psi is a chart, so invariant by gamma. So that's something. If you have something like that, then this turns out to be the quadratic holomorphic. So this one, not that one, but this one turns out to be the quadratic differential. Yeah, because yeah. So what I wanted to say is that in this coordinate, so this is Beltrami. No, I didn't use the word. So this should be the complex dilatation. So in this affine map, the K was the complex dilatation. Okay. But for this map, this is a complex dilatation. Okay. So so if you define phi z to be this one, then this becomes the phi bar divided by this. And you get the equation in the theorem. So what I wanted to say is that so if you just look at the affine map through a chart, which is invariant under the covering translation, then what you get is this complex dilatation. And this is nothing but the definition of the complex dilatation in the theorem by Taichimura. So in other words, what Taichimura constructed is a affine map with respect to the local chart. So he showed that if you have two Riemann surfaces, the most efficient quasi-conformal map is a locally affine map. So it's obviously this cannot be done globally because they are Riemann surface. And the quadratic differential must have zeros. So because you have a holomorphic function on Riemann surface, so it has zeros. Okay. And around zero, so you cannot do the same construction. But still, you have so if it has zero, then you have a chart like that. So you have a union of the something like a rectangle around. This is a zero. So it is a point when phi is zero. Still, you have a affine map on that part, and that part. Okay, that is the most efficient map. So that's what Taichimura tried to show, and he proved that it's actually the most efficient one. So that's what I wanted to say. So So this distance, so dihumular distance, is realized by some particular map, which is called the dihumular map. So the maximal dilatation of the dihumular map, and well, maybe the half of the log of the maximal dilatation of the dihumular map is equal to the distance between the two points on the dihumular space. That's what I wanted to say. So thank you very much. The time is